Everybody. So we're going to do a little example here of finding the distance from a point to a line in three-dimensional space. And if you look around certain textbooks online, there is a rule or a formula that can be developed for this problem, and that's fine. And especially when we're new to three dimensions, I know working through it's weird that we live in three-dimensional space, but we have a very hard time picturing it sometimes, or we can't really draw it, which makes it really hard. Um, so I'm going to try to develop this answer using more sort of geometric intuition so we can practice picturing how these things are working. So in this example, we want to find the distance from a point, in this case 3, 0, -4, to the line given as a vector equation, r of t, that you can see there from it's the vector 0, 1, -1 plus t times the vector -2, -1, 1. So I've drawn a sketch of the situation, and I am not at all trying to be accurate. All I need is, or all I think I need, maybe I'll discover somewhere along doing this that I need more information in my drawing. It's not working well enough. And in that case, I will change it. But for now, I think this is a good sketch to get me started. I'm going to make these lines a little thicker, I think, if I can. I thought I'd be able to. I don't. All right, they're good enough. There's the line, there's the point. So first of all, let's think about what we mean about the distance. Right? It depends on where you measure from. And so the obvious place to measure to, I think it's obvious, is the distance so that along a line that is perpendicular. If you draw the line from the point to r of t, we want it to hit r of t perpendicularly. Like whatever room you're standing in, look for the nearest wall and ask yourself how far away you are. You'll look in a perpendicular way at the wall. So that's kind of the obvious notion. Turns out that's going to be the shortest distance. So in this case, let's put this in. That's going to be this distance. Okay. So I'm just going to name it whenever there's something that I know I need. Let's call this distance D. This is the distance from the line to the point. Okay. So I'm going to think about vectors. Okay. And what I might want to come up with is the vector from this point, between this point and the line, right? If I knew this vector, let's make that a little thicker. If I had that vector, I could easily find the distance. So let's give that vector a name, and let's just use the d we've already used. So now the vector d, its magnitude is equal to the letter d, right? So the letter d is the scalar, which is the magnitude of this vector d that goes, it's perpendicular to the line r of t, and it spans that distance, okay? So we need some way to get at this vector. So here's an idea, okay? So, and there's no clear way to say how maybe you might come up with this. It just sort of, I don't remember how I first came up with this idea to do this, but just playing around with some of the geometric notions we've had got us here. So here's my idea. I'm going to pick some point on the line. I can find a vector from that point to the point in question. Okay. Now let's give this vector a name. I'll call this vector u. Okay. When I have that point, I might be able to use this vector to help me understand the vector d. And the way I'm going to do that is, if we remember from the dot product, one of the things we were able to do with the dot product So here's, oh, let me label this. Here's the vector v, which I'm just using to be the direction vector of the line in question. Right? I'm going to just imagine taking that vector v, I'm going to make a copy of it and move it over here. Okay. So one of the things we might remember is that with the dot product, we were able to work out a way so that we could grab another color. Ooh, how about bright blue? We can use the dot product to come up with the distance that I've indicated in the drawing, right? It's the different places call it different thing. It's like the projection of u onto v. Remember, this is a copy of v right here. This distance here, let's call it L. And I'm not going to go through this derivation, but if you remember from the dot product, if I take u dot v divided by the magnitude of v, I get this distance. Okay. Then I can take that distance and multiply it by a unit vector in the direction of v. Okay, so there's a lot of symbols here, but let's look at what everything is. This parentheses, inside the parentheses is the unit vector in the direction of v, right? So maybe v is longer than 1. So there would be a unit vector in the direction of v. We take that unit vector and scale it by this length that we're talking about. This is going to give us a new vector in the direction of v that is the distance along this line of the project. It's like this vector is the projection of u onto v. That's how I should say it. It's like the shadow of u on v. Okay, and I'm calling that vector L. Right. Again, the magnitude of L, I'm calling just the letter L without the vector notation. Okay. Now, from this picture, notice L plus D is equal to U. Right? If I add the vector L, that's a vector. Just do a little sketch of this up here. L is a vector like this. D is a vector perpendicular to it in that direction. That gives us U. Right? So that's just a little sketch of what's going on in this triangle down here. D is the thing we're looking for. So D is going to be U minus L. Rather, the magnitude of D is what we're looking for. So we could take the magnitude of D if we had it. So do we have everything we need to get D? Well, we have V, that's given, right? That's what L is. Do we have U? We need, so in order to have, we don't have U, I guess is what I'm saying. We'll have L once we have U, but we don't have U. What do we need to have U? U is a vector from a point on the line to the point that we were given. I can choose any point on the line. The simplest point to choose is the one that R of t is pointing at when t equals 0. In other words, I'm going to choose 0, 1, -1. You could put in something else. You could put in t equals 1,000 if you want. It just makes all your calculations harder. So I've chosen probably the simplest line or the simplest point that I can. Maybe there's a simpler one. It looks like we can get some cancellations if we wanted to. I'm just going to take this point. So this means U, we can now figure it out, is going to be right? Just we know how to find vectors between 2 points. I'm going to take the point 3, 0, 4 and subtract the components of 0, 1, negative 1. So this is the vector 3, negative 1, negative 3. That's the vector u. Okay, so now what does this mean? Looking again at our formula for d, the vector d, it's equal to u minus l. U we just figured out. L only requires us to know u and v. There's a bunch of computations we still have to do, but we have all the information. And now it's just a bunch of addition and division and multiplication and so forth. Once we have d, we can find the magnitude of d, which is what we were looking for all along. So let's go ahead and finish this up. So if we've got u, to find L, so here is our formula for L. Let's work out what L is. So I'm going to come up here where I have a little bit of space. L is equal to, well, let's just figure out the pieces first. So first I need u dot v. That should be easy enough to figure out. U dot v is equal to, let's see, where is u, where is v? Oh, I covered them with my screen. There we go. U is equal to 3, negative 1, negative 3, dotted with v, negative 2, negative 1, 1. So we get 3 times negative 2 is negative 6. Negative 1 times negative 1 is 1. Negative 3 times 1 is negative 3. So we end up with negative 8. So u dot v is negative 8. I'm going to need that. What else do we need? And while we're doing this, I'm going to rewrite this. This is, I think, often how this formula is presented. Magnitude of v squared times the vector v. Keeping in mind, this thing in front is a number, a scalar that we're scaling the vector v with. So let's figure, we need the magnitude of v squared. So the magnitude of v squared is just the sum of the squares of its components. So this is going to be 4 plus 1 plus 1 is going to be 6. So the magnitude of v squared is 6. This makes L equal to 6. Sorry, u dot v is negative 8 divided by magnitude of v squared, which we just figured out is 6, that we're multiplying by v. Negative 2, negative 1, 1. And let's just rewrite this a little more simply. So this is going to be negative 8 times negative 2. This will give me a positive. We can do some cancellation. So this will be 8 thirds. Negative negative gives me a positive 8 sixths, or let's reduce this. This is silly. 4 thirds. Sorry, I just, oops, I guess the first one I can't. 8 thirds. This one is 4 thirds. This one is negative 4 thirds. Okay, that looks like our the correct values. Okay, so that's L. D is going to be U minus L. So U was 3 minus 1 minus 3 minus 8 thirds, 4 thirds, negative 4 thirds. So we'll have 9 thirds minus 8 thirds is 1 third. Negative 3 thirds minus 4 thirds is negative 5 thirds. Negative 9 thirds. That's the only negative. Okay. Negative 9 thirds plus 4 thirds, because we've got minus minus, is going to be negative 5 thirds. Again, let's double check that. 9 thirds minus 8 thirds is 1 third. Minus 3 thirds minus 4 thirds is minus 7 thirds. Oops. This is what I get for skipping steps. Negative 9 thirds minus minus, so plus 4 thirds is negative 5 thirds. This is the vector D, which means the magnitude of D is 1/9. I'm just squaring all these. 49 ninths plus 25 ninths. So what does this work out to? We'll have 50, we'll have the square root of 75 ninths, or 5 root 3 over 3. Or 5 over root 3 if you'd like. Either one is fine by me. All right, so now if you look up the formula, right, formulas are pretty simple, but I think, and there are different ways to derive it. This is the way I've done it. You can use the cross product and some facts about parallelograms to do this. That's another interesting intuition around this. I don't think you can see it quite as well. You have to believe that fact about cross products, which is true, but sometimes it's hard to understand why. But in any event, I think this is a perfectly reasonable way to go through this problem, and it makes us, look at the pieces of these three-dimensional lines and this three-dimensional space, and kind of get to know it a little bit better. Okay, that is it for this one. Thanks, everybody.